First of all, let me welcome you to this afternoon's lecture. I'll say a word about the lecture. This is the inaugural lecture in the C.N.R. Rao Lecture Endowment Series. The lecture series has been created following an endowment by Professor C.N.R. Rao, and this enables us to bring to the Institute some of the most distinguished scientists in the world. So I think the Institute is particularly grateful to Professor Rao for this gesture, and I hope that over the years this lecture series will be something that we will all remember. A word about Professor Rao also. I won't introduce Professor Rao or the lecture series except to say this, that Professor Rao's association with the Institute goes back more than half a century. And in the many years that I have known him, in different fora, he will always say, our institute. He's been associated with many institutes, so you don't know which institute he's talking about. But it always turns out that when he says our institute, it is the Indian Institute of Science. And although Professor Rao was taken away for a little while from the institute by the IIT at Kanpur, it turns out that the institute was never taken away from him. This afternoon, we are particularly fortunate to have Professor George Whitesides as the first lecturer in this series. We couldn't have really found a more distinguished lecturer, and his field also is something that is quite appropriate for the C.N.R. Rao lecture series. Professor Whitesides did his PhD a long time ago with John Roberts at Caltech and was on the faculty of MIT for many years before he moved to the other institution in Cambridge, that is Harvard University, where he's been ever since. Professor Whitesides is one of the most distinguished chemists in the world, and he has been very widely recognized. I will not mention all the honors that Professor Whitesides has received. His work covers many, many different areas of chemistry, extraordinarily interdisciplinary in nature. He's received the National Medal of Science in the United States, the Kyoto Prize. He received the Dan David Prize in Israel along with Professor Rao. He's received one of the American Chemical Society's highest honors, the Priestley Medal. And he is, of course, a member of the US National Academy of Sciences. But I will say only one thing. In recent years, scientometrics has become a very popular field, and the H-index has dominated the discourse of scientists. And here, Professor Whitesides holds the record. His H-index, I will not mention it here, because I don't have it, is a score which Sachin Tendulkar would be proud of. Professor George Whitesides.
I am particularly happy to be here to start this lectureship, which honors C.N.R. Rao. I'm particularly impressed by the fact that C.N.R. Rao's had the foresight to name the lectureship after himself while he's still alive. It's this kind of foresight which I think C.N.R. Rao is being particularly good at. And I should tell you just one story about Professor Rao. I was taught how to do chemistry by a man named Jack Roberts. And some of you are old enough to know Jack Roberts probably. And he has the characteristic that he is unable to say, not to say what's on his mind, whatever it is. He says what's on his mind. This is just background for my first encounter with C.N.R. Rao, which came when I was here first and sometime in the 90s, first visit to India. And I came and I wasn't feeling very well. And over the course of the first couple of days, I developed some bumps on my neck. And after a while, the bumps fused and became large blisters. And I mean, it really was a mess. I was disgusting to look at. And normally what one tries to do is simply to go home, pretend it isn't happening. But I thought this was a bad idea. I went to Professor Rao and I said, I bother you, but I think I should see someone. Fine, we've arranged it, It's now noon, at 1:45, you have an appointment. I said, how did you know I was coming? He said, well, we've actually had this person lined up all week. We were having a great deal of trouble getting distinguished foreign visitors to come and lecture in India. We thought that if you died here, that would make it work. So I felt immediately at home, because that's exactly the kind of thing that Jack Roberts was saying, what he said when he was trying to be tactful. So thank you, Professor Rao, for saving me on that occasion. Thank you for being a friend over many years, for being one of the great synthetic chemists and great explorers in chemistry, and for making this lecture so possible. So the lecture today is going to have only a little bit to do with our research and more to do with the subject, which I think is extremely interesting for chemistry in general and for Indian chemistry in particular. And it is, in brief summary, the following. This is what I'm going to tell you. That chemistry has done a terrific job over the last 50 years in a particular style, which I think is now at an end. That's point one. The second is that there are probably more opportunities in things related to chemistry, which depend on chemistry, than there have ever been at any time that I've been a chemist. I can't imagine a better time to be a chemist. But that the definition of what chemistry is may have to change to accommodate those opportunities. And then the third point is that in reinventing chemistry, you have to ask, where could the invention take place best? And the period between World War II and now has been dominated by the United States and by Europe. If I look at the problems now, I'm not convinced that the proper place to do much of this science isn't in India. Now, it's going to take ambition and skill to do that, but it's something I want you to think about during the course of the lecture. So let me start with some observations to set the theme. This first is numbers from the United States. In the US, over the last 20 years, there have been 300,000 jobs lost in the chemical industry. Globally, over the last 10 years, there have been about 300,000 jobs lost in the pharmaceutical industry. And the question that you ask, looking at those kinds of numbers, is chemistry over with? I mean, have we done our thing? Is there anything left to do? But it doesn't make sense. You look around, you look outside, it's getting warmer, you think about water, you think about energy production. It doesn't make sense that we're at an end of things. And let me just quickly give you a couple of pictures to set the scene. This is, of course, a diagram of inputs and outputs for the energy sector in the United States. This represents fossil fuels. Here is nuclear, here is solar. These are the contributions. Here are various things output. It's not important what they are right now. But what is important is to understand that there are an enormous number of interesting problems there, not necessarily the ones that you might think. So for example, there's almost endless work being done on solar energy harvesting. I have yet to convince myself that solar energy harvesting as a form of power going on the grid makes all that much sense one way or another. But that's the kind of issue to think about. This is the cost of a long life. This plot, this side, and the bars are life expectancy from 82 to 74. In this side, you have the number of dollars spent per person in various countries in order to achieve this life expectancy. So this blue line. Now there are two, I think, really interesting features of this. The first is that if you look at the expenditures of things, there's a particularly interesting point here and here. This is the United States, this is Cuba, and they have exactly the same life expectancy. And in general, I think what one can say is that there is very little relationship between the amount of money that you spend on healthcare and the outcome in terms of this particular surrogate for the quality of healthcare. And by many standards, U.S. healthcare is actually not terrific. The other more interesting way of looking at this plot is to say that everyone, regardless of how much you spend, lives about the same length. We live to be in the order of 79 plus or minus a year or two. And you can draw from that the possible conclusion that no matter how much you spend, the medical profession actually isn't doing anything. And there are actually strong arguments even within the medical profession that that's right. And you see me here, I'm presently 73. 100 years ago I would have been dead. But I'm not living to the length that I'm living because of end-of-life medical practice. I'm living my current life because of clean water, clean food, antibiotics, vaccination, things of that sort, what we call public health. And this is one of the things I want you to think about. The difference between our current model of end-of-life treatment versus a possible different model in which we devote our attentions to public health. Those are practical problems. Here is an intellectual problem. That's a cell. And the question that I would raise with you to think about, this cell has the characteristic that it's alive. And I will argue that that question of what is life, where did it come from, is the great intellectual problem of this 100-year period. Last period was what's the structure of matter and what's energy. I think it's now a very different character of life, very different character of question. And I'll phrase this question in a way that I find compellingly interesting. It's compellingly interesting for me. And that is that a cell, we know, is a lipid sac, which is made of molecules, which are filled with molecules, and the molecules are reacting, and every once in a while, they get stuff from the outside, and every once in a while, they undergo a paroxysmic event in which the cell divides in two. So it's a stably self-replicating, dissipative, out-of-equilibrium system. We don't understand anything about any of what I just said. But the point that's interesting is that we know that this collection of things is made of molecules, which are not alive, undergoing reactions, which are not alive, and the ensemble is alive. And how does that happen? And we have literally no idea what goes on. I mean, no intellectual conception of what it is to make this property called life emerge from a collection of molecular reactions. And there may be some of you who are biologists here who say, well, that's not really a chemical question, it's a biological question. And I would argue very strongly that it's purely a chemical question. Biologists are wonderful at the observations that lead to this, but the underlying understanding of emergent properties in networks of chemical reactions is something that only chemists. So, wonderful intellectual problem. And then here's an example of something in which India clearly has closer contact with than many other countries, and that is this fundamentally new human construct, very recently emerged, called megacity. And we define megacities as cities of 50 million people or more. It's a purely arbitrary definition. But what's interesting about megacities is we have zero idea of how to manage them. We know how to manage small cities, but we don't understand large cities. And generally, when you're taking something that's very complicated, you have to break it up into pieces. And the pieces here are mass transport, so food into the city, water into the city, waste out of the city, energy into the city, propagation of information and viruses in the city, things that are complicated like education, which we don't understand, spreading and changing the city. Many of those questions actually map on concepts in statistical mechanics and chemistry. And so putting together an architecture all the way from understanding the basics to thinking about what the sensors will be that make things work here will be very, very interesting and very chemical. Now, in 2007, I went to Avignon, where I was at a conference on ethics, and I was out of place there, but that's neither here nor there. But this group of ethicists was interested in the question of what is the ethics of nanotechnology. And we immediately reached the conclusion that there were no ethical problems in nanotechnology. But there were a series of other ethical problems which were really quite interesting and worthwhile thinking about. And the conclusion that surprised everyone was that they were all chemical. Now, by contrast with what? The contrast was, let's say, in the last century,
You could argue that the Schrödinger equation, with the invention of nuclear weapons and with the internet, transistors, and all the rest of it, it was that that changed the world. And maybe not, genetic engineering, understanding how to read the genome, changes our understanding of things in an equally important way. But the problems that we presently face are actually chemical questions. And I raise it because chemists tend to think about what they do in small scale. That is, we make paint, we make drugs, we do stuff like this, rather than large scale questions with very broad arguments. So the questions come up, if this is all about problems that are not exclusively chemical but have a chemical component, who's responsible for solving them? And in particular, a question with ethicists are obligations to whom for what. And these are just examples. I'm sure that many of you would come up with a very similar list. But for example, taking care of the globe, global stewardship, climate variability. Those are technical questions which are sensors, analysis, mass transport, that kind of thing. Healthcare, which is critically important in equity and justice. The issues here are lowering costs, raising the effectiveness, distributing the benefits, anticipating, having a system that's basically set up for social return rather than for capitalist return. These are certainly chemical questions. Jobs I'm going to come back to later. And you have this kind of list. They're easy to make, but the question of what sciences have to be involved, what technologies have to be involved in making them work is largely a chemical issue. So what we do is big stuff. And then at the same time, there are these wonderful conceptual questions like what is life? How do we think about megacities and other dissipative systems? How do we understand emergence and complexity? How does life come from something? These are tremendous opportunities. So one could look at the past. And chemistry has had an absolutely fabulous 50-year run. And I'm sure you all would agree with all of these things. Total synthesis, structure determination by NMR and by X-ray, catalysis, drugs in some cases, the limits in single molecule spectroscopy, environmental maintenance in terms of catalysis, and 100 others you could put down there equally well. So if all that's going so well, you can ask the question of, is there a problem? And what is the problem? And I gave you part of the symptom of that in saying that there are massive job layoffs. So something is not working perhaps as it should. Now the problems are not entirely to do with science. They a lot have to do with broader issues of the world as it is now. For example, we now have a dominant ideology, if you want to think about it, known as capitalism. And at least in the US, in its purest form, capitalism basically recognizes short-term financial return and gives no value to long-term social return. Just doesn't care about it. And that means that when you have a problem like global maintenance, which is not necessarily profitable, how do you develop the technology? Who pays for that? And it's not perfectly obvious. If you're trying to reduce the cost of the healthcare system, that's absolutely contrary to the Novartis, Roche, Merck kind of model. It's a different model where somehow society has to pay for it rather than companies paying for it. We don't really know what this means. In this world, and we can argue about it, the owners of large companies actually assign negative value to long-term research. That is, if you're doing long-term research on interesting problems with real potential, they say shut it down. And the reason for that is that money spent on research is money not given back to the stockholder. And then there are some other things, such as much of the technology that was developed in the last 50 years ultimately can be traced back to defense spending, and the Cold War period is gone now, and it's been replaced by what's known in Washington as the Long War, which assumes that we will have unrest at about our current level of distress of maybe the next 100 years. So, interesting problems. Globalization in jobs, the lowest cost provider wins. Information, IT has changed everything. Universities are trying to figure out what they're doing. And so it's just an immensely interesting world. Now, universities. You are in a university, I work in a university. What is a university? And it's a good idea to understand that the research university, so-called, which you are in and which I am in, is a very recent invention. It was developed in the United States after World War II. And it was based on a particular model which said that a country needs universities which have the technical capability of laboratories like IBM and GE in order to provide for national security. And a very important document by Vannevar Bush called The Endless Frontier actually set the agenda globally. Everybody follows this same kind of argument, but with distortions. Bush was pretty clear in this document that the purpose of research universities was to deal with three very practical problems. That is, create jobs, or create the technology that creates jobs, contribute to public health, and contribute to national security. It was never intended that universities in this view follow curiosity. That just wasn't the issue. So what we have now is something in which we have a real split in universities between people who say, leave us to do what we want to do purely for curiosity, because out of that approach comes things like quantum mechanics, which have enormous application, which is true. And then others who say, we're paying the bill, we want to see something for it, which is another point of view. And both are legitimate, but they're different. Another point about chemistry, which makes it particularly interesting, is that chemistry has always had a intellectual connection with industry, which is tighter than most people, I think, realize in terms of creation. The players in invention of things are basically universities, government, industry. And the basic model, the simplified model, was that universities invent, industry innovates, the government pays here and regulates here, and there's a kind of flow of ideas from university into industry. That's actually wrong. Some of the most important ideas have originated in industry, not necessarily in university. And I'll give you some examples, and I do this in a fashion that academics can approve of by talking about Nobel Prizes. ROM, which was a Nobel Prize, was actually originated in Shell and practiced at the level of millions of pounds per year in something called the Shell triolefin process in the 60s. Now, it was developed in universities, but it was actually invented in industry. And actually, much of the intermediate work went on in DuPont. Asymmetric ethoxidation was invented in industry, made L-dopa. Superacids came from George Orwell looking at the way olefin crackers worked. And they involve passing hydrocarbons over what are called superacids, very, very strong Lewis acids, which are silica alumina. And George asked the question of, can I replicate that kind of behavior in a liquid medium, and which he proceeded to do. So all of these are terrific things. NMR spectroscopy was invented in the university, but it would never have had the impact it has had it not been fully developed as a package of ready-to-use software in NMR in industry. So there are many things that have come from universities, but the connection between industry and university has been very close, both intellectually and in terms of implementation. Why do I go through this? And the answer is that industry is now out of the business. They didn't do it. It stopped, for reasons that I'll discuss in a moment. But we've got to figure out what to do about that missing piece of the invention cycle. And here is, for better or for worse, one of the really major driving forces in fundamental science, if you want to put it this way. And it is your generic curve of cash and time and risk discounted cash flow. And for those of you who are graduate students, I want to just walk through the basic ideas here. You can find them all in the first chapter of any accounting textbook. But it's very important to understand what's going on. Imagine that I have an axis here, which is time. And in this direction is money coming in, and in this direction is money coming out, going out. And I start a research project at this point, and let's say for the sake of argument, I develop a product and start selling it about there. So what happens? At the beginning, money's going out, so I have to get money in. The way you do this formal analysis is that you say that the money that you're spending there, regardless of where it comes from, you consider that you're borrowing it and that you have to pay interest on it. So it simply accumulates, the amount accumulates, and the amount that you're paying interest on it accumulates. At this point, you begin to get some revenue from the sale of your product, And after a while, the costs of running the research die away. But you're not getting very much money here, and the interest payments are getting more and more. Eventually, the integrated amount of money here is equal to the integrated amount that you've spent there, and there's a crossing, and you become profitable. That's the argument. Now, why is this interesting? And there are two extremely elementary rules that come out of this. One is that the shorter the time from here to here, the better. So large industry, which is financially driven, cannot afford to do long-term research and doesn't anymore. And the second thing is that you have to consider that what comes out here depends upon your evaluation of the risk of the project failing. And the closer you are to the end, the more timid you are, more realistic you are in choosing your project, the less likely you are to have it fail. So that you discount the results in terms of risk. Risky projects are ignored. You discount in terms of time. And the consequence of that is a large company, basically. Large companies are basically out of long-term research. That's not going to change. Something else will have to happen. Now let me just give you an example of this to give you a sense for timelines. This is for a particular technology, which some of you will be familiar with, called MEMS, microelectromechanical systems. They are the micromirror system that runs the projector. They're the three-axis goniometer, three-axis accelerometers and cell phones. There are a lot of uses of these things. But if you look at 10 or so technologies and look at the times between discovery and cost, full commercialization, the average time is almost 30 years. And for the times that are ones that were slow, like this one, oscillators, the time from full commercialization to invention was almost 50 years. So these times are very long. You pay a lot of interest over that. And that's what people are concerned with. You need to get to the end result. The argument goes faster. And that doesn't seem like a good idea for climate change or restructuring the healthcare system, where you're not going to do it in 18 months. Okay. One other background point I want to make. This is something else that chemistry is a little bit lost track of. We tend to phrase discussions in terms of research and development or science and engineering. There's actually a third activity, which is not science and it's not engineering, and it's called discovery. People who are good inventors, who come up with first ideas, are often neither scientists nor engineers. One of our primary sources of inspiration now is YouTube. You go to YouTube and you find people putting on YouTube the most incredibly stupid things that you can conceive of. I mean, riding their motorcycles naked off the roof into the swimming pool and that kind of thing. But if you look at some of those, you find that they're incredibly interesting at the same time. And because they've found phenomena that are big enough and interesting enough, and often simple enough, that they could do them, they could put them on YouTube, and people look at it. So it's a real source of inspiration. It's the equivalent now of going to the library and just leafing through old journals. So we find all kinds of interesting stuff on YouTube. But in any event, we do the science well, we do the engineering well, but we don't actually do very much with invention and discovery. Industry doesn't do it, and universities don't do it. So it's something we need to relearn how to do. Now I want to finish this section with this quote from Phil Bryson, who writes sort of popular science in the United States, and he's a very clever guy. And he points out something which is problematic about the country. This is, I'll read it for those of you who are at the back. It says, physicists are notoriously scornful of scientists from other fields. That's true. When the wife of the great Austrian physicist Wolfgang Pauli left him for a chemist, he was staggered with disbelief. Had she taken a bullfighter, I would have understood, he remarked with wonder to a friend, but a chemist. And as I found somewhat to my horror in the United Kingdom, the news reports talk about the sciences of chemistry. And it's part of the same thing. You know, we present ourselves as others little helper. And that's not the appropriate stance right now. Okay, so what's the future? And I think what's going to happen, I know it's happening in the United States, and I think it'll happen globally, is rewriting the social contract. That is the following. We in universities mostly get our money for research from government. And the deal has been, We, government, give you research. You, in an undisciplined way, do whatever you want to do. You put this up on the shelf in the form of papers, and then somebody comes along and figures out what it's good for. And I think people are reaching the conclusion that this is not a workable model. So instead, the story, I think, in the future is going to be, we, society, have a problem with climate change, with AIDS, with the cost of healthcare, with whatever it is. You and universities, if you'd like to work on it, we'll be happy to pay you to do so. And by the way, if you want to take 20% of the money and do the fundamental science that you need to do that, we understand, and that's terrific. But we actually want to know that you're working on something with the direction. This is a fundamental rewriting of the way university and society work together. So this gets to the issue of obligation in the ethical sense, that is following the money. The way it works right now is that taxpayers, which can be either individuals or corporations, reluctantly give money to government. And they do so because A, if they don't, they go to jail, and B, there is some idea that if the money goes here, the government will spend it on something that will be for the public good. The government gives an insignificant amount of that to universities. And the idea is the universities are supposed to come up with good ideas which go to corporations, which are the only entities that have the muscle to actually produce products and benefits, and then the benefits benefit the taxpayers. That's the idea. But very broadly, I think the notion is that if these people, whoever works in the supermarket, is paying you, you actually have an obligation to do something for them. Not in a general sense, but actually in a pretty specific sense. And there are many people who disagree with that, but this is going to be a really big issue. So the present and the future then comes down to a couple of things that are pretty interesting. Almost unlimited practical problems to solve. Climate change, healthcare. Almost unlimited opportunities that are purely driven by curiosity, like origin of life. But neither of these is necessarily what we call chemistry. There's something else. So we've got to reinvent, hence the title of the talk. Now this discussion is perhaps oversimplified in the US in terms of this plot. This is called the pastoral quadrant plot. The idea is that you take a 2x2 thing of this sort, and on one axis you put the quest, how important the quest for fundamental understanding is, either not or high, and how important utility is, possibility, low or high, and give it a name. So Bohr, it is claimed, did what he did with Bohr atoms simply because he was curious about how atoms worked and how spectroscopy appeared. Edison strung strings of everything between two sources of potential to figure out which one gave the most light. And then the one that's interesting is this one, the pastoral quadrant, where the argument is that what you can do, and what is actually harder to do than either of these, is to pick areas where there are very highly important problems to be solved, for which there is no science that provides the basis to the problem. So you pick an important problem and you solve it by inventing new science. And that's probably the way we're going to try to solve it. And agencies like DARPA work on that basis now. People who don't like this basic notion have a way of looking at this when they say, that's nonsense, what's happening here is just that all you're doing in that quadrant is applying known science to incremental improvements. But the better way of doing it is to say that you're identifying really big problems and inventing science to solve them. And I have a little warning for you. And the warning has to do with this sector. And that is, in many places, that sector where there's low interest and low utility is called the university sector. And you don't want to be in that situation. That's not, as we say in the States, that's not good branding. Now, what about quantum mechanics? And the argument for quantum mechanics has been that it's hard to find anything that's more important, Maxwell's equations, quantum mechanics, and the periodic table, but recently quantum mechanics. Hard to find anything that's been more important. I mean, the internet, Facebook to nuclear weapons is basically all quantum. And it certainly came purely out of curiosity. It was not directed toward anything. But there were two characteristics about it that were important. One was this was very small scale science. This was a small number of European scientists who basically their entire budget was paper. And they did it almost as much as a hobby as anything else. And so for very small amounts of money, you can afford to do anything. The second thing I would argue with you is quantum mechanics is a once-in-a-century event. I can't think of anything else like quantum mechanics. And you can make an argument perhaps for genomics, but it hasn't really happened yet. We've learned a lot, but it hasn't made very much difference in the practical world. So quantum mechanics is a one-off. But then the argument about quantum mechanics could be, quantum mechanics represents science as art. And shouldn't we be appreciative of the art of science? Yes, we should. But there's a financial test here. And that is that if you're going to say that science is like art or sculpture or writing novels, and you're going to then put it in a category in which it deserves the same kind of financial support, public support, as ballet or writing novels or sculpture. And the thing is that the amount of money that goes into the arts almost everywhere is so small relative to what's required to keep the scientific establishment afloat that it won't work. So you can phrase your science, if you want, as art, but you have to expect it to be paid for that way. So I think that's a losing proposition. Now let me make another point to you, and this is sort of a pasture-product thing. I think if you think about many of these problems, and think about them as either science forward or problem backwards, you actually can't tell the difference between the two. So, for an example, third world, Africa primarily, really poor developing stuff, requires new medicine. India, this picture is from India, but India is a very bad example because the Indian system ranges all the way from being among the best in the world to being non-existent. This is developed world public health, if you want to think about it. This is home health care. You can think about that kind of thing as being something in which there's a very practical objective. But if you think about how actually to do it, how to connect new technologies and the underlying science that goes into the new technologies, where cost is important, to science and engineering, early stage engineering, the problems are immensely interesting. And so I can think about this in either senses. We've talked about this. There are obviously big, interesting practical problems, but also at every stage of this, there are problems in fundamental science. How do you, just to take an example, which is a very interesting one, if you look at energy from petroleum, from natural gas, and from coal, it represents about 85% of global energy production. If I could increase the efficiency of heat transfer in a boiler from the flame to the heat transfer liquid by 1%, I would do more than you could do with everything else put together. How do I do that? I don't know how to do it. I don't know. That's why it's science. So if you look at these things, you can't tell the difference between radical engineering and radical solutions of problems and fundamental science. Megacities. One of the things that we'll have to have in megacities is a network of sensors that monitors everything and reports so that the city managers, the city brain, will know what's going on. What are these sensors going to be? How are they going to put together? What's the information flow? How do we think about that from an information point of view? Fundamental science. So a very practical outcome, but very fundamental problems. And I remind you, those of you who are involved in this, that one of the heroes of information technology was Claude Shannon. Claude Shannon developed essentially all of the theory that's presently used to describe transmission of bits in binary. And Claude Shannon had the specific job of efficiently transmitting information down a copper pipe, a wire, with maximum retention of information. I mean, he was not doing basic statistical mechanics of information. He was doing information transmission. So you don't worry about whether it seems practical or not. Ideally, it should be both. What is life? You say this is a very intellectual problem, and it is, but if I can find ways of having systems of reactions which become self-evolving in a Darwinian sense, I will absolutely radically transform chemistry. I will not do this, but I hope some of you will. And then, this is a small example, but an interesting problem. The pharmaceutical industry is going into the mountainside right now, financially. going out of business because it can't invent new drugs. It just can't do it. There are a lot of reasons for that. But one of them is that there is an old model which says if I have a protein and I know what the active site is and I fit my drug to the shape of this, then I'll be able to rapidly hand the job to CNR, who will synthesize it because synthetic chemists can do anything. The trouble with that is that probably this model, intellectual model of lock and key, is wrong. And it's not, in fact, the contact between the lock and the key or the ligand and the protein that determines anything. It is, in fact, the water that's in the empty lock is high in free energy, and when a ligand comes in, it displaces it. Fundamentally different picture. It's not protein-ligand interactions, it's water. So, everywhere you go, there's something interesting going on. So, what's next for chemistry? And one possibility is a revolution. I think it's necessary. And what makes for revolutions anyway? There are two theories of revolutions. One of them is that if you have new tools like NMR or PCR or tunneling microscopes, they make for revolutions because they make it possible to make new discoveries. The more interesting one, we all agree on this. The more interesting one is this argument for intellectual necessity, which was highly popularized by Thomas Kuhn in arguments about quantum mechanics. And what he says basically is that scientists are, like everybody else, bone lazy. And having a revolution is extremely tiring. So you don't have any revolutions just for fun. You have revolutions only if you have to. And you have a revolution then when theory and experiment are fundamentally incompatible. That's the only one. And he makes a very interesting point, which is very relevant to chemistry, which is that what he does is separate problems that scientists work on into two categories. There's a category which he calls a puzzle, and this is his definition of a puzzle, but I want to phrase it slightly differently. A puzzle, he says, is what 99% of scientists work on. And puzzles have the characteristic that you know that there's an answer to the puzzle. You know roughly what the answer is. You know how to get there. Nobody cares about the answer. And you do it because it's technically fun to do it. Then there's another kind of thing, which he calls a puzzle across a problem, which is, his examples are cure for world peace or understanding where life came from or things like that, where the characteristic is you don't know there's an answer, or you don't know there's an answer that you can get to, you don't know how to get there, you don't know what tools to use to do it, but people really care about it. And there are very interesting arguments about why it's okay to have the 99% working on puzzles in order to get to the 1%. But what I think we're interested in is problems, the 1% that really count. So what I want to do is to begin to finish by talking about three problems. Two of them, paper diagnostics and robots, we've worked on. One, we worked on CO2 and made no progress. And I'm not arguing that these represent the right way of doing it. I just want to give you an example of, in this kind of problem, where we put our money and why. So, CO2. We all understand that CO2 is an enormously important molecule. What you may not have thought about is that if you think of all the simple molecules, CO2 is one, H2 is another, O2 is unbelievably interesting because of the spin state problem, N2O, NOx, we don't know anything about them. We stopped working on these many years ago. So we're now in a situation where we need to do something, and we don't have any of the tools to do it. And an example of a problem is this one. We have a financial model for the hydrocarbon industry in which you start with crude oil, and which is basically fully reduced carbon. You strip off hydrogens, and then you use an inexpensive oxidant, which is oxygen, to make intermediate oxidation states of organics. Here's something like that. And this is the way we use about 10% of the world's energy and about 5% of, 10% of the world's hydrocarbon, 5% for hydrocarbon product, and 5% for energy. Now we're entering an era, maybe, in which we will have for the first time a pure source of carbon, that being CO2, which has a negative value. That is, people will pay you to take it. And if this is cheaper even than this, you can think about using more expensive reducing agents to get to that. You say, oh, that sounds very interesting. The interesting thing from the point of view of universities is that, in fact, we don't know how to do it. There is no practical chemistry which gets you there. So this represents an appropriate university problem. How do we develop new chemistry for O2, CO2, CO, N2O, whatever? Start from scratch and rethink the entire industry from something other than this as a starting point, but rather electrons and CO2 and so on as starting problems. We've tried it, we can't make too much progress with it. Healthcare, zero-cost diagnostics. One reason I'm here in India right now is that we're putting together a pretty substantial program with Samir Brahmachari and CNRS, this CSIR, on zero-cost diagnostics. And the notion here is, how do you provide diagnostic services at the lowest cost for both of these kinds of applications? And the particular approach that we've taken is to say that we're going to use what we call paper chips. And this is just the operation of one of these. This is the chip. It's two pieces of paper sandwiched between two pieces of plastic with some lines printed in it to divide the paper into regions that are separated. Put a drop of blood on this side, a membrane wicks out the erythrocytes, the serum goes through, distributes it to these various pipes, and you read colors. And why is it interesting? Well, it's interesting because the clinical laboratory test for this particular function would be somewhere between $50 and $100, and the chip costs somewhere in the order of a penny, and could be made much less expensively. The stimulus for this was not to ask what the science was that was most interesting, but what was the science that would make it cheapest. And what we settled on was using printing technology like newspapers and comic books. And we've added various features to that. So we've gotten into a bunch of stuff. This is an example of one of the print chips. And what is interesting here is that we started this project in 2007, and in 2012, which is 5 years later, we have it in field trials in Vietnam. And that's relevant because it's very hard to go from a laboratory first demonstration to reality unless you think about something that's really cheap and really simple. So the idea is basically a good idea. But it also leads to new science in other ways. And I'll just point out without too many details that if you build a three-dimensional stack of these things, so I have here, just take this spot. This is all hydrophobic by printing. That's hydrophilic. I put a drop of something in here. We use here a piece of literally carpet tape, just double-sided Scotch tape. Fluid goes through here into another patterned piece of paper, flows to there, goes through that hole, separates into these pieces. Each of those goes into that, separates into those pieces, and comes out there. What you see is that. So what you have is the ability to make a three-dimensional microfluidic system which operates without power at a flexibility that you can't do with open channel systems molded in plastic. It just can't be done. We've done a lot of that work, and we can say that tomorrow. And so here is what you would get if you took 10 microliters of serum and divided it into 1,000 wells. And in principle, each of those wells can be a different amino acid. So if we can make this work, we will have revolutionized the cost structure for that particular world. All right, here's the third of these examples, jobs and robots. Why do I care about this subject? What's the large-scale problem? And the large-scale problem is jobs. And the issue here is that if you ask what the competition is between nations, what are we competing for? And I'll argue with you that we're not competing for resources or land or any of that. We're really competing for jobs. Because with jobs, we have economies and young people have places to go living in society and go to work. That's all good stuff to do. But we phrase it typically in an oversimplified version of saying it's high wage rate versus low wage rate countries. So it's US versus China and India, or US and Europe versus China and India. And we really make a mistake because there's a third party in this, which is coming along more rapidly, which is robots. And let me just show you, I want to do this here and that. I want to show you my example for this is something called Big Dog, which is intended to be a pack animal. And I want you to look at how it walks. So that's something in which it's being kicked there, and all of that complex motion of the limbs to recover balance and restore equilibrium is done without a brain by simple gyros. It's just a collection of gyros and feedback circuits. And that passes to me the Turing test. That is, I can't tell that that isn't a lie. Just mechanically. In other senses, yes, but I can't tell in that sense. And if you look at it going uphill, in a moment it will come down. There's one here, right in here. If you watch it slip there, that looks so much like an animal, I can't help. Now, take that and add on it the processing capability that's coming from computers. When you talk to your computer now, you mostly talk to a voice recognition system, and it's getting more and more sophisticated. It is not going to be long before we will have people we have robots that are certainly as intelligent as simple animals and moving rapidly toward you. Right, so our stimulus for our program, our totem, is this marvelous creature. And this is the squid, octopus. And I want you to watch how it manages to get out of that little hole. It's a pretty big octopus. And it pulls itself out, and in a moment it's going to have a little tugging match to get its brain out. The brain is soft. And then the rest of the octopus out. And I like to go all the way to the end on this because with great tugging and pulling here, finally gets out off. And it is, to me, a look of great self-satisfaction at that point. But this makes robotics not a question of mechanics, metal rods, motors, things of that sort. It's all now a question of elastins. And so, how does one do this? This is now a chemical problem. And let me show you two examples. This is from our soft robots program. Here's an example of something that's very easy to do with soft robotics and very hard to do with a conventional robotic gripper. And what is happening? That's an uncooked egg. There's just one pressure system that allows it to reach down and do that. So it grips the egg without cracking it, lifts it up, and very straightforward. But at the same time, there's this kind of behavior. It's the same hand. And this is something that also can't be done with a hard gripper, that's a hammer. And I'm whacking the hand. I always wince when that happens. And to convince you that this is real. And now, it works. So you try to do that with a hard robot, it's a bit smart. We take these things and we drive cars over them. It doesn't make any difference at all. And you can actually get some fairly interesting behavior. Some of you heard this at the beginning. It's just more fun, but it's not for fun. And this isn't entirely trivial because to get a key to depress, you actually have to have rapid motion and you have to have a fair amount of impulse in that to drive the hammer down. This is not, it's not as straightforward to do as you would think. Okay, so what do we do? Let me finish. So, the good stuff is that there are an immense number of problems. The solutions to most of these really interesting problems require chemistry, so new chemistry is the same. So chemistry is on the table. No problem. The bad part is that we've evolved into greater and greater intellectual community. We're very risk-averse. Financial return basically says that industry isn't going to do any more research, and the teaching that we do focuses on the past rather than the future. Who's going to do it? It has to be universities, because industry, for better or worse, has to live with capitalism. And it basically has the job of exploiting knowledge, not creating it. The government just really can't do anything for all kinds of reasons. So we have the freedom to have some flexibility, and we can choose to work on problems rather than on puzzles. We can choose. what we have to do is, I think, redefine chemistry. So it now has a definition that takes in all this stuff, not just what we've historically done. Teach in a different way, not to have graduate students be technically competent, not asymmetric catalysis, but to actually have breadth and creativity. We need to find a mechanism for taking fields that have been productive, that have worked well, and reached the end of the road and kill them, not let them drag on. The remark in the U.S. is that you can never get someone to change their opinion, you can only wait for them to die. And this is in this category. You can never get old academics to take on new fields, you just wait for them to die. Make collaborative R&D the norm, and I'm going to come to that last point about poetry in just a moment. Teaching. The thing that's so interesting about teaching to me is that the way we teach chemistry, and I should say I teach big undergraduate classes, has the characteristic that what I teach, I know it's archaic, it's outdated. I know that it's often wrong, and I teach it anyway. Certainly it's non-demanding, there weren't reactions. And it's arguably not very relevant to these problems. Aside from that, it's probably terrific. So what's an example? We teach the carboxylic acids are stronger acids than alcohols because of resonance delocalization of the animal. No, doesn't have anything to do with that. It's probably mostly salvation and the inductive effect of the oxygen. We teach that benzene is more stable than cyclohexatriene, hypothetical cyclohexatriene, because of resonance delocalization. No, it's the sigma framework. We teach that iodide is more nucleophilic than bromide, is more nucleophilic than chloride, is more nucleophilic than fluoride, when actually fluoride is more nucleophilic than chloride, is more nucleophilic than bromide, is more nucleophilic than iodide. And what we're doing here is confusing solvation and reactivity. So why do we do it? And the answer is we largely teach out of textbooks. And the textbooks are designed to sell, which means they're phrased at the lowest possible denominator. And that's, you can argue it's okay, and every subject has to start somewhere. And I think this problem is going to be fixed by simply putting everything on the web. People who make textbooks think that textbooks as an issue are dead at this stage. But it hasn't happened yet. So we need to reinvent education, particularly at the graduate level, to reduce specialization, let people move around intellectually difficult subjects, and get people, even synthetic chemists should be learning thermodynamics and applied math and systems theory and information and all the rest of this. Because if they can't do it here, in graduate school you can learn hard subjects. You can't learn hard subjects when you're out working for a living. It just doesn't work very well. You don't have the time. And then we still have a system which is based on the Liebig model. It's an apprentice system. We are largely teaching students to be like us. And what we should do is to teach students to be not like us, different than us, better, we hope, but anyway, different. But this model is saying, professor has an idea, assigns it to a student, assigns the idea to the student, so the idea is pre-formed. The student performs the technical work to do whatever is necessary. They publish a paper or a thesis, and then what largely happens is the student goes off with the same idea and assigns that to another student. And there's a kind of propagation of bad ideas that occurs. So the idea of teaching students rather than using students is something. Now, two final slides. One is for those of you who are students. And you listen to all this and you say, nah. He doesn't face the problem of going out and getting a job and getting money and getting grants. And that's all true. But what I want to do is give you my final 2x2 McKenzie game theory matrix for how to succeed in an academic world. And it's based on the idea that you can have a problem that's either important or unimportant, and you can either succeed or fail. Now, most people say, at least consider the idea that what they should do is think that the most important thing is to succeed in the problem. But let me take you through the results. This is what you do in game theory. If you have an important problem and you succeed, you get a lot of credit. If you have an unimportant problem and you fail, then you get no credit. Right. So it's the off-diagonal terms that are interesting. And if you have an unimportant problem and you succeed, you get no credit because nobody cares. It's like unimportant. On the other hand, if you have an important problem and you succeed, you actually get a lot of credit because you open the door. And nobody succeeds in the first round. So the best thing to do is take an important problem. Pick the problem for its importance and get started. Throw yourself at it. It'll be okay. Everybody admires young people who pick difficult problems and go at it. Nobody expects you to succeed in the first 3 years. Now, the last issue is poetry. I always admire the physicists who manage to take things that are absolutely inhuman. Exploding stars, black holes, these gigantic cosmic blowtorches, quarks, chromodynamic objects, whatever, and somehow make them feel interesting. They're really, really good at that. So, I admire the branding if I don't necessarily know what to do with the other things. Chemists are terrible at it. So we say, we make paint. Toothpaste. How do you know this? And one of the better ways of doing it is to show your affection for nuclear weapons. Generally, that really is okay. But there's another way of doing it, which is to say, well, I'm a chemist, and what do chemists do? And what chemists do is, let's say, make statins. Well, what's a statin? Statin is a compound that blocks HMG-CoA reductase and acts as an anti-inflammatory. It's a major source of sales for the pharmaceutical industry and a few other sentences. And you look up, and whoever you were talking to is gone. It's left. Good thing. So what happens if you don't want that to happen? And you simply say, it's just sad to change the way we die. And then you got them. You know, they're with you all evening, and they want to know. And so there are lots of things of that sort that you can do. But it requires thinking about chemistry as something which is really unbelievably interesting. Reality is unbelievably interesting. Chemistry is a big part of it. And if we think about it as toothpaste, it comes out as toothpaste. So, terrific stuff. I am extremely happy to be here to honor Ram Rao, who has been an innovator in trying to think about new things for chemistry to go into. We want him to be around for another 4 years, but we want him to think about new things to do. Thank you very much.
Thank you very much for a really exciting lecture. I'm sure all of you will agree that it's been a real exciting tour de force, really, to think about so many things, not just in the context of chemistry, but the way we conduct research. Is it possible for me to have a couple of questions? I think if there are two pressing questions, really, because I think the speaker has really charged the audience, and so I think if there are really just two questions that you would like to ask Professor Whitesides.
Yeah, you can, those of you who are not reading the subtext, what that says is Professor Whitesides has gone on for too long, so it should be two questions.
So, are there any questions? If there are no, then I think we'll have a chance to meet with him again this at tea, and we bring up questions with him to ask. So let me thank Professor Whitesides again for this fantastic talk, and let me invite Professor Balram to honor him with some bouquet, and we have a few photos.
In terms of poetry, you can do a lot with red roses.
What a lecture. Sandwich What are the questions were in that?
And that's what makes it a great chemist.
So thanks a lot. It was a brilliant first lecture. What a treat.
And to me as well. It's a great pleasure to be here.